In this video, I want to take a look at using variation of parameters to help us solve second-order non-homogeneous linear differential equations. Okay. So, here's my first differential equation, y double prime plus y equals tangent of t. Now, if I want to find the general solution to this differential equation, then I need to find the general solution to the homogeneous equation and one particular solution to this equation. Now, this I pulled this out of the textbook. This is, I think, number 2 in the homework set. Anyway, they give that t is between 0 and pi over 2. In everything that we do here with these differential equations, we are looking at the intervals. You know, the existence theorems say that you have unique solutions in an interval that contains your initial condition. When you get outside of that interval, then the functions can be discontinuous and you don't necessarily have unique solutions, but at least within an interval you do. So what this is doing is just restricting t to be within the interval that's all these functions are continuous. Tangent has, vertical asymptotes at the odd pi over 2's. So we could actually be, I think, between minus pi over 2 and plus pi over 2, but for whatever reason, I think they also want the tangent to be positive. Yeah, so anyway, in this interval. So in order to solve the non-homogeneous equation, we have to first solve the homogeneous equation. So this is one that you can just almost look at. You know a function whose second derivative is equal to minus itself? Yeah, sine and cosine work that way, right? Because the second derivative would be minus themselves. If you did it with the characteristic polynomial here, you'd have r squared plus 1 equals 0. So r is plus or minus I. Anyway, sine and cosine are my two independent solutions of the homogeneous equation. Notice that the Wronskian of y1 and y2, there's my two functions, take their derivatives, take the determinant, and I end up with minus 1. So the Wronskian is minus 1. So the method of variation of parameters is I'm looking for u1 and u2 that I'm going to multiply by y1 and y2 respectively, add them together, and end up with a solution to the non-homogeneous equation. Okay. And in the last video, we saw that the solution is that u1 is negative g times y2, so u1 goes with y2, and then divide by the Wronskian, integrate all that. So that's what I have here. Tangent times cosine, tangent is sine over cosine, so the cosines cancel out and you just have the integral of sine, which is minus cos t. Yes, there's a plus a constant. I don't need all of the possible u's that will work here, I just need one, so I'm taking the constant to be 0. Likewise, now u2 was g times y1 divided by the Wronskian of y1 and y2. And so sine times tangent divided by y1. Anyway, I've got a minus sine squared over cos. This takes a little bit longer to integrate here. I changed the sine squared t into 1 minus cosine squared t, distributed the minus 1, distribute the cosine in. I've got the integral of cosine t minus secant. Cosine integrates to sine, and the secant integrates to the natural log of the absolute value of the secant t plus the tangent of t. And now that interval comes into play here. I don't actually need the absolute value sign here because from 0 to pi over 2, sine, secant and tangent are both positive. If you add them up, that's positive. I could just use parentheses instead of absolute values there. Anyway, so my yp is u1 y1 plus u2 y2, which, what happens here? There's a cosine t and a sine t multiplied together, and there's a minus cos t sine t, so those cancel out, leaving just the cosine times the log there. I guess there's a minus sign in front of it. So minus cos t, natural log of secant t plus tangent t. I want to actually verify that this is a solution to the homogeneous equation, the non-homogeneous equation, right? So I need to find the first derivative and the second derivative. Well, it is a product, so here's your product rule. First times the derivative of that natural log, well, that natural log came from integrating the secant. So if you take the derivative, you get back to secant. So cosine, negative cosine t times secant t plus the derivative of the negative cosine, which is the sine of t, times the natural log of that. So there was the product rule. And notice the minus sign became a plus because the derivative of the negative cosine t was positive sine. Yeah, so cos t times secant t is 1. So that's minus 1 times this. Now take the derivative again. The derivative of 0 would be, derivative of minus 1 would be 0. And then you got another product rule. So there's sine t times the derivative of that log plus the derivative of the sine times the log. Right? Notice that the sine times the secant is tangent. So tangent of t plus this. Now, is it true? Is yp double prime plus yp equal to the tangent? That was the original differential equation. Does it work? And there's the second derivative, and there's the original function. Yeah, those two things cancel out, leaving just a tangent. So indeed, we have created a monster. No, we've created a solution to the non-homogeneous differential equation, which means the general solution to that non-homogeneous second-order linear differential equation would be the general solution to the homogeneous equation, so c1y1 plus c2y2, plus the solution to the homogeneous equation, and it's minus just because yp was minus, so I'm adding that negative. And there you have the general solution to the non-homogeneous equation. Okay, let's try another one. Let's just roll this up here. We've got y double prime minus 2y prime plus y equals e to the t divided by the quantity 1 plus t squared. Again, we have to start by solving the homogeneous equation. So I put a 0 over here. This is second order linear with constant coefficients. So I'm assuming a solution that looks like e to the rt. Plugging that in, of course, we get the characteristic equation here, which happens to be r minus 1 squared, leaving only one solution being r minus 1 squared equals 0, leaving only one solution, r equals 1. So that gives me e to the t, and then with methods that we did before, we know that the other solution is t e to the t. So the two solutions to the homogeneous equation would be those two. We can check the Wronskian of those two. Is, what's that, y1 times the derivative of y2, there was a product rule there, and then minus y2 times the derivative of y1. There's a t e to the 2t and a minus t e to the 2t, which disappear, leaving just an e to the 2t. So this times that, giving us the e to the 2t. So now we are looking for a particular solution to the non-homogeneous equation of the form u1 y1 plus u2 y2 with the y1 and the y2 actually plugged in there. Okay. According to what we did in the last video, u1 is going to be the integral of negative g times y2 divided by the Wronskian, which, what happens? The e to the t times e to the t is e to the 2t, which cancels with e to the 2t on the bottom, and I'm just left with the integral of minus t over 1 plus t squared, which I would do a u substitution with u equal that denominator, 1 plus t squared, so du is 2 dt, hence 2t dt, and I got the t dt. And what happened to the minus sign? There it is. So then, of course, the plus c again, I don't need the plus c because I'm not looking for all the solutions, I just need one. So I'll take c equals 0. And y2 then is g times y1 divided by the Wronskian. In this case, the two t's, the e to the 2t's cancel out, leaving just the integral of 1 over the quantity 1 plus t squared, which would be an arctan of t, or an inverse tangent of t. Remember, the u1 and u2 were created so that we would multiply each one by y1 and y2. So the u1 times y1 is right here, and the u2 times y2 is right there with a plus sign in between. And then the general solution to the non-homogeneous equation is the general solution to the homogeneous equation plus the particular solution that we just created here. Okay. So there's a couple of examples of using variation of parameters to find particular solutions to non-homogeneous second-order linear differential equations.